Thank you all for the kind introduction. My name is Eiichi Funatsu from OMNIVISION. Today I talk about the evolving landscape of automotive image sensors. So here's the agenda. Let me start talking about who is OMNIVISION. So OMNIVISION is an integrated circuit design company, and main business of us is image sensors, and that is in overall categories, including mobile, PC notebook, automotive, security, emerging, and medical. And we have the synergy in each of the applications. For example, we started the high IR sensitivity technology, NIXL, in security segment. We applied that to automotive. Or we started the global shutter in emerging market and applied to automotive and so on. We started HDR development in automotive, and we deployed to security, mobile, and so on. And we are in the automotive market from 2005, so we are having the 20 years of experience in automotive market. And overall image sensor market, share point of view, we are number 3, simply because we are actually number 3 in mobile market. The mobile market is 2/3 of the overall image sensor market size. But actually, in the other categories, we are overall number 1 in 80 other categories. And that includes the automotive market. So let me start talking about the main part, camera acquisition status. We started the automotive business from the rear view sensing. Then gradually, we have increased the cameras in automotive. Next stage was to add the front-sensing camera with rather low resolution. Then we have the front view system, and front-sensing, rear sensing has more resolution. Then finally, recently, we have front view system and all of the ADAS system, including front-sensing, side-sensing, and rear sensing cameras, plus in-cabin 2 cameras. That's the latest situation that requires 11+2 cameras in each automotive in high end. So I talk about some topics in each of the cameras. First one is the front sensing. Of course, the most hot topic is LFM, or LED flicker mitigation. Here I show some example of the high dynamic range technologies in the market. On the left side, it's an old one. We started from the multiple exposure and multiple frame solution. We have the long exposure, medium exposure, short exposure in each frames. The problem was that each of the exposure timing was very different. That introduced some ghost in the HDR image data. Next, we had the staggered HDR. Then the timing difference gets smaller, but still different timing. And recently, we have more and more traction in the single exposure HDR solution that is applied to LFM, LED flicker mitigation. And in that, we have several technologies like LPD, SPD, DCG, or LOFIC technologies. LPD, SPD case, we make use of different sensitivity of large photodiode and small photodiode. And DCG and LOFIC, I show something in the next page. So left side is showing the principle of zero converger gain. We make use of high converger gain and low converger gain. Many of the cases, the sensor guys make some analogy of the photodiode and fluid capacity by bucket size and water. Now we have the highlight condition. The bucket is filled with a big amount of the photo charge. Then we transfer this photo charge into the floating diffusion bucket with the same size as the photodiode to measure the voltage swing. In the low light condition, we don't have that big amount of the photo charge in the bucket. So we transfer to smaller size of the bucket to have decent amount of the voltage swing. That's the principle of DCG. In LOFIC's case, the low light condition corresponds to the highlight side of the DCG. That means the photo charge is fit into the fluid capacity of the photodiode. In the much higher light condition, the photodiode will overflow. Then this overflow charge is captured by the much bigger bucket, that is LOFIC. One drawback of LOFIC is that we have more noise, flow noise, with this capacitor and some connection. But if we can make use of those technologies to have the exposure time long enough, then the pulse to flicker LED is mitigated. And each of the technology has some different exposure HDR ratio, like 4 to 10 or 10 to 50x. And we apply that to, we actually have the combination of these technologies to apply to the product. And for example, these are the things we see in the market for 2.1 micron automotive sensors. On the left side, we see so-called single photodiode LOFIC technology. And in that, we combine HCG, LCG, that means DCG technology, plus LOFIC, plus VS means the staggered HDR technology. On the middle one, we combine HCG, LCG, that's DCG, plus SPD means LPD, SPD technology, plus LOFIC. On the right side one, we combine HCG, LCG, and SPD, small photodiode is directly connected to LOFIC, so they don't have the SPD output. So all of these things have some pros and cons. Let's say on the left side, in the sensitivity thing is the best because we don't sacrifice the large photodiode area by small photodiode. And the center one has the best performance in LFM D range because they connect the SPD to LOFIC. That makes it easier to expand the dynamic range. On the other hand, the center one uses a 4-channel to be used in LFM range. So including a VS to make it 4-channel, the left side still has the highest dynamic range. And in terms of the temperature condition, left side one has the best performance because the dark current affection to the LOFIC node is less with the higher fuel capacity of the large photodiode. So overall, this is the pros and cons we have, and we apply that. And maybe in the future, we may have smaller pixel size LFM sensor. Then probably the left side one has easier to scale to a small pixel. Now I show some example of the LFM sensors data, old one and latest one. You see the old one is not high enough D range in LFM, so you see the signage is flickering. On the right side, it has high enough LFM D range, so you don't see the flickering in the signage. And for the future, front sensing sensor for ADAS. So what is required? Maybe one natural direction is to have higher resolution with smaller pixel size. Like currently it's 8 megapixel, maybe we go up to 18 megapixel with 1.4 micron. The other thing is that, of course, we want to have even wider LFM dynamic range. Or the other thing is that recently we have some contradictory requirements. In LFM solution, we try to have the exposure time long enough to mitigate the LFM flicker. But that long exposure time leads to motion blur in the high-speed moving object. Customers started complaining about that. So how to solve that? We actually still don't have the final answer for that. We may need to read out with both of long exposure and short exposure to do both of the data, or we may make use of event vision sensor type of technology. Long and short exposure is obvious, but maybe event sensor is not very obvious to you. So I just talk about some basic concept of that. So in event vision sensor, it detects the change of the light amount to the photodiode, and without the integration concept. So this graph shows the vertical axis is the log domain of the input photon amount. And if the contrast is getting higher, like a higher and higher photodiode amount, then it fires as a positive fire. Then if the light amount gets reduced, then it fires as a negative fire. Then each of the pixel has that kind of fire, and that gives some right side picture like performance. Then in the CMOS image sensor, we have the integration type of the output, and it's a dispersed output. So CS has a high resolution plus low temperature information. So EBS may be able to fulfill this gap between this sampling time and sampling time of CIS to fill this blind time as a CIS. That may be used for motion blur mitigation or be used in recognition. So here's an example of the recognition performance based on some simulation data with standard EBS data. Left side is showing for the case with 20 FPS CIS data. And the right side is showing the 1/3 of the frame rate of the CIS with the help of the EBS data in between this 7 frames data. It has the kind of same performance in recognition of the object. Especially at the center of this image, you see some bicycle coming out from the sign, traffic sign. And that's kind of a generating of the new object in the image data, intermediate of the 2 frames. But because of the help of the EBS data, this right side can have the right recognition of the bicycle with the right timing. The next thing is a combination of the function in the side sensing camera. So I talked about some future direction of the front sensing sensor. Maybe we have 18 megapixel sensor. Then can we apply that high resolution to the other cameras? Maybe one example is that we may apply that to side sensing camera. And this side sensing part, we don't require that 18 megapixel resolution. So we may output with a quarter resolution for that. And then combining with the e-mirror function, this e-mirror part requires high resolution. So we output with a much higher resolution, like 18 mega equivalent resolution for that part with narrower FOV. So that may be one example of the combination we may have in the future. The other important combination have a traction in the market is this always-on function. Recently, people want to have some kind of surveillance-like function in automotive when the car is parking. In order to prevent from the burglary, people want to do the surveillance around this car. So we want to keep the camera on. But the problem is that in order to keep the camera on in the current system, the camera is on, the main SoC is on, the interface, so the interface is on. So it consumes too high power, like 15 watts. Then the idea is that, OK, you may add the always-on function to the camera. And the camera can let the main SoC sleep during the time. Then if the camera finds something around the car, then it wakes up this SoC. And also it has some pre-recording to send out to the SoC. Then the effective power can be 0.1 watt or something. It's a big improvement of the power consumption. The basic concept is shown here. So at the left side, you see low resolution image data with low frame rate. It's always on mode, and the SoC is sleeping. When it detects something, then it wakes up the SoC and send out the pre-recording data, and also send out the normal function data, like a full resolution and 30 FPS. And here's an example of the data captured. So you see currently the low resolution data, and it's actually low frame rate. And when this guy is coming close, getting to normal frame rate and high resolution. And this guy is doing suspicious, but don't worry, this is our engineer. Now, the next one is a sensor modeling thing. So these days, automotive customers want to develop, let's say, autonomous driving. That requires big amount of development, especially for the system and software. Then they also want to start the development even before they have the hardware car. So they cannot run the car thousands of miles. So how to do that? They need to do the development based on some simulation system. So they require the sensor vendor to provide some sensor model to be used in that development. So we have the image sensor model. That model includes, let's say, color coding, overall noise or HDR function, and so on. Then the platform vendor should give us the scene information to project the sensor. they also need to set up the sensor like a gain and exposure time or some temperature condition. Then the sensor model do this include the noise thing, and then do the HDR combination, and adding some cybersecurity or metadata, then provide to the backend side, the system for the simulation. And here is some example of the data. On the left side, show the input image data in the HCG, LCG, low-back channel, and we combine to the HDR data and provide to the backend side. And here's some real-time simulation data based on CUDA platform. So you may feel like, OK, this is just some computer graphics animation. But the main difference is that this is done by projecting the scene image data to the sensor model, and we have the adding noise and so on, doing the HDR combination, feed back to the backend side, and this backend side reproduce this ISP pipeline. That's the difference. OK, the last part is the metrics. So we are sensor vendors. And normally, we evaluate our sensor based on SNR, signal-to-noise ratio. High SNR is better. But is SNR enough for automotive customers or not? That's the question. For example, on the right side of image data, you can see some tonal image data. And eventually, the right side of image data may be having higher SNR. But the problem is that with this high SNR image data, you cannot see the car, because this high SNR is done by the fog. So this one example of the problem. The other thing is low light condition. Normally, let's say in the mobile market, we want to achieve a high SNR under low light condition by applying the noise function. Many of the cases in automotive customers, especially for machine vision application people, they don't want to have the denoise. They prefer noisy low light data, rather keeping the original image data, rather than high SNR with blurred image data. So how to think of the optimization of those things is the question point. And there are several people working on that in the market. The first example is shown in the IEEE P2020 activities. The left side is showing some contrast patches. And if you see your sensor has too high noise, then at some patches between patch to patch, you cannot differentiate the gray level anymore. And if you have the high enough signal-to-noise ratio, you can see the more tiny difference of the gray level. And right side is showing the example of the data they have. It's similar to SNR curve, but the difference is that the vertical axis is a contrast amount, and each of the color means how much we can easy to differentiate these two patches. And each of the contrasts corresponds to some condition of the input objects condition, like a white object in front of the white car, or dark skin color person in front of the white car, and so on. So, the upper side, so this is a comparison for the two low-fix sensors having good high temperature performance or bad high temperature performance. And the upper one has better high temperature performance. So you can see many of the objects can be easily seen in this case, but the lower one has some trouble in some high temperature, like 105 degrees C. The last one is the other metrics. This is trying to capture more, take this resolution thing into account. So MTF is a major component for the resolution, modulation transfer function. And there are two major proposals in the market I see. One is from image engineering, so-called noise equivalent quanta. The concept is that, so the denominator is consisting of two parts, noise power spectrum divided by the average output level. That's kind of a SNR thing, and that's applied with MTF, the power. So it's kind of a multiplication of MTF times SNR in the power to make by making square. And then the IMA test also proposed similar thing. And this is based on some mathematics theory from Shannon. They proposed so-called information capacity. And eventually, this concept is similar to noise equivalent quanta. It's kind of an integral of NEQ in the spatial frequency domain. So we may have a chance to have the right criteria from this kind of thing to take object contrast and noise and resolution to camera things in the future. That's for machine vision application. Okay, out of the conclusion, we have more and more cameras in the each cars, like up to 13 for now, maybe more in the future. And we have more diverse requirements for camera and sensor developments. Of course, generic requirements are higher sensitivity, higher speed, lower power, and so on. In automotive specific, we have LFM, and motion blur is another thing we need to take care. And combination of functions like always on is another thing happening. And sensor modeling is another important thing to have the automotive vendors develop with a software system development. And we have the new image quality criteria seeing the market for mainly for machine vision application criteria. Thank you for your attention.